Hello and welcome to our continuing series of science sharing webinars in Central Region. I'm happy to introduce today's speaker, Matt Bunkers, who is the SU at WFO Rapid City, and he will be speaking on cyclic mesocyclogenesis, and sounds like it's going to be a great webinar today. Matt, it's all yours.
All right, well, thanks, John. I thought I'd put a picture up here since we don't meet face-to-face anymore, and at least those of you who haven't met me can see who's talking to you, and throw tomatoes at your screen if you so desire. I want to mention three things. First of all, this is a review of other people's work. I'm not presenting anything original. None of this is my research. It's just a synthesis of some papers that I read and wanted to bring that together. Secondly, there's several offices that have a lot more cyclic mesocyclones than we do here in Rapid City. So if you want to, you correct me on anything that I say or have some insight to share based on your observations, please go ahead and do that. And then finally, Mike Myers, if you're on the call at Grand Junction, you have my permission to shut your door, turn out the lights, and take a nap for the next 30, 40 minutes because this isn't terribly applicable to western Colorado. I don't have any animation, so hopefully the slides will show up pretty well here. I want to start out with just an example of cyclic mesocyclogenesis, and this is the upper right is a picture of a couple tornadoes northwest of Zurich, Kansas, in June of 2005. The photo is from Chuck Doswell, and it actually I retrieved it from a paper Bob Johns and others just published on the Tri-State Tornado in the Electronic Journal. Anyway, it just shows a pretty classic example. You have your supercell here on the left, and I have the 2 points where there were the tornadoes. You can see the hook here. The red or the southwest dot is where you had the tornado that was beginning to dissipate, and then the new one to the northeast of that, which was just developing and strengthening. So pretty typical classic example of what we're talking about here. I was motivated by three people, actually. First, Phil Schumacher in Sioux Falls and I were going back and forth about an interesting case he had in his area. Joshua Scheck up in Bismarck then on another case, another day, chatted with me about cyclic mesocyclones, left track tornadoes, and then Ken Cook finally sent me this. So to me, the moral of the story is if three people come to you independently and ask you about a topic, you better, A, know something about it, or B, if you don't know anything about it, you better find something out about it. So that finally got me the critical mass to start looking into this. Before I talk about cyclic mesos, I think it's important to note what is not a cyclic mesocyclogenesis. And here we're talking about low-level mesocyclones. There's a lot of these cases where I'm sure you've all seen it where you have dual supercells or mid-level mesocyclones, where you have two supercells fairly close to each other. The reflectivity may or may not be touching, but this is not considered cyclic mesocyclogenesis. And I have two examples on the following slides. In this first example, we're looking at last June in southwestern South Dakota, and the storm ocean was to the southeast. And if we look at the left here, there are actually two distinct supercells, and I've drawn some outlines of the broad reflectivity of the storm. And so you can infer that there's somewhat of a little inflow notch on this northeastern one, and then also the same thing on the southwestern one. And indeed, when you look at the velocity on the right, you see cyclonic shear circulations with both storms. They were persistent temporally and spatially, so they were clearly two distinct supercells. Eventually, the circulations went on to merge in the southeast, to the southeast of this location, and produced a significant tornado. Of course, if you've ever seen Morris Wiseman talk at COMAP, he's pretty good at drilling into your head that that vorticity is additive. So when two vorticity centers of the same sign merge, it will actually strengthen. So, but that, again, this is not cyclic tornadogenesis or low-level mesocyclogenesis. This is two distinct supercells, and it could be a talk and topic all in and of itself. In this next example, we're looking at a case, fairly famous case from the first vortex that Conrad Ziegler published in Monthly Weather Review, the so-called Graham-Newcastle storms. And again, this is the storm oceans to the southeast, and this is a conceptual rendering of this case study. And this dashed line outlines the broad reflectivity, so you can kind of see one supercell to the southeast, and then another supercell to the northwest, and you can see the hook on that. So again, they're somewhat connected in their reflectivity. The T's represent where there would be a tornado in the event that there was a tornado. The typical supercell location in the hook area, and then another tornado on the gust front. The only tornado in this case happened to be the one with the northwestern supercell in the classical position. And so this wasn't cyclic tornadogenesis, it was just two supercells very close together. And it's not always the rear one that produces tornadoes, sometimes it's the front one, and there can be interactions based on the outflow from the first one. Again, that's way beyond the scope of this talk, but I just wanted to indicate what it is not, what we're not talking about here. So going back through the research, Don Burgess put forth a conceptual model, which I'm sure many of you are familiar with. This was back in 1982, 12th Conference of Severe Local Storms. It's a classic model, and by and large, it stood the test of time. I'll just go forward through this figure here and explain that. Actually, this large box that we see is a blow-up from what you see in this little inset here that tracks Tornado 1. So initially, it started out with a supercell mesocyclone core, and what they called low-level wind discontinuities. Essentially, you had your rear flank gust front and then your forward flank gust front. And with time, you have a surge in RFD that begins to occlude. You develop a tornado. That's what this gray track here is, the tornado. And eventually, the storm continues to occlude, and eventually it gets to a point where the first mid-level mesocyclone turns left, and you have that familiar left turn to the tornado track, and then you have discrete development of a new core to the right of the first mesocyclone. And then, because that's in a vorticity-rich environment, and goes on to produce tornado fairly rapidly after that. And so Don Burgess and his co-authors looked at 41 mesos. About 25% of them were considered multiple cores. So if you have two cores, you ended up with one cycle. Typically, they had 3 cores, but they had one case that had 6 cores. And the subsequent cores developed rapidly and over a large depth of the atmosphere fairly rapidly. And they noted that the RFD tends to wrap cyclonically around the meso and cuts off the inflow. There's some observations that contradict that, but this was what they found in their study. Now, this was the one key figure from Don's paper. This next slide shows the next key figure, shows the average evolution of a 3-core mesocyclone. So time goes from the left to the right. On the top, we see the reflectivity extent from 0 up to 16 kilometers. So you see, broad development of the storm, pulsations in the storm top, and then decay. For the mesocyclone core 1, you see relatively long organizing stage, long mature stage, and then dissipating stage. And the red bars here indicate where you have the tornado. So you see with the first core, first of all, it takes a while for the core to develop, even though you have a thunderstorm, and then it takes a while for the tornado to develop. But subsequently, you have fairly rapid development of tornadoes with the next cores, because as the first core is dissipating, the next core is already going through the organizing and mature stage. So rapid subsequent tornado development. Typical lifetime of their first core was an hour and a half with 45 minutes of subsequent cores. Don Burgess went on to state that for long-track tornadoes, there may be this delicate balance of forces in which the gust front doesn't get too far ahead or accelerate around the vortex. So he's kind of implying there's this balance between this inflow and outflow, which was fairly prescient from him, because a lot of the more recent research is suggesting that sort of thing. So we'll look at that in a little bit. So after Don Burgess, there was quite a bit of time that elapsed before people looked at this in detail. Adlerman out of OU did some modeling work in 1999, did some numerical simulations of this, and basically what they came up with in their study was classifying occlusion as five steps. And so we'll go through this figure here. You have A, B, C, and so forth. And for each letter, you have a surface depiction and a mid-level depiction. And the surface I just have highlighted here with a green box just so it stands out. And so in these pictures, you have the cyan, which represents updraft areas. You have red, which represents positive vertical vorticity. The dark blue would be downdraft areas, and the yellow would be the reflectivity outline, and then the black barb line, the rear flank gust front, and the forward flank gust front. So anyway, at stage 1, you have a supercell where the RFD develops, and you're starting to get initial mesocyclogenesis in the low levels. Stage B, you see a pulse in the mid-level updraft, and at the surface, the RFD continues to intensify. You see a hook feature in the reflectivity field. Stage 3, you have occlusion, a strong occlusion downdraft, with the low-level mesocyclone being separated from the gust front occlusion point. And obviously, you could be having tornadoes occurring at this time. A little bit later, stage 4, they have decaying of the mid-level updraft and the mesocyclone drifting rearward, but at the same time, there's some new mesocyclogenesis occurring in the low levels at the occlusion point of the gust front. And then finally, after that, the old supercell is essentially gone. You have a new supercell, and the process starts all over again fairly rapidly. Essentially, what this simulation from Adlerman and others did was reinforce the results of Burgess. They also noted in their study, a paper that they referenced, the Starkow and Roos, I believe, that a little under 0.25% of their tornadic storms had this cyclic behavior with intervals from 20 minutes to 2 hours. So quite a range there, similar mean to what Don Burgess had shown. So a few years later then, Adlerman and Drogmeyer did another study on cyclic mesocyclogenesis, and they just simply were looking at the sensitivity of model settings to cyclogenesis, cyclic mesocyclogenesis. And what they found were that just simply by changing the grid spacing, things like microphysics, diffusion, surface friction, had dramatic effects on the number of cycles and the evolution of the cycling. This figure here just shows one example from their paper with tracks of the surface vorticity for different grid spacings. So, for example, at the 2 kilometer delta X, they had one low-level mesocyclone, you can see here in black, and that was it. When you went to 1 kilometer delta X, you had 3 cycles. You had the C1 that did a loop like this, and then C2 that came over like, did another little loop, and then C3 that actually was moving southeast. And then at 0.5, you had, again, very different kind of evolution. You had C1 and C2, which went along the same general path as just C1 did previously. So the moral of the story here is just little changes in the modeling produce dramatic differences in the cycling. And I've dabbled with cloud modeling a little bit, and I've noted the same thing, just small tweaks. Sometimes even running it on a different computer platform with the same settings can lead to different results. So that's not terribly surprising to me, but it does illustrate the difficulty in getting to these kind of details. Well, then around the same time, or shortly after Adlerman, David Dowell and others came out with a study, and I think Howie Bluestein was part of that. This was a vortex case. I think it was the McLean, Texas case from the first vortex. They came up with modifications or suggested modifications to Don Burgess's model. The thing I really want to stress about this is it's only one case, so it's hard to come up with a conceptual model from one case, but it was a highly observed case with aircraft and mesonet and radar and so forth, so they did come up with a conceptual model for that case, if you will. And they found in this case that the rear flank gust front didn't actually advance ahead of the mid-level meso, as in the Don Burgess's model. They noted that the low-level meso tend to form at the gust front bulge and not the occlusion point, which would be back in here. So that was one difference they noted. They also noted that the main updraft, mid-level updraft mesocyclone persisted and didn't go through a cycling. So even though you had low-level cycling going on, the main mid-level updraft continued to move northeast. Another thing they noted that in this case, the tornadoes moved to the left of the storm track for the entire time. It wasn't just as the tornado was occluding that it all of a sudden took that left turn. But otherwise, they did note how if you look on the right panel, we see that the dark gray was areas of updraft, the speckling as downdraft. So as you had one occluded mesocyclone in the low levels, another one was developing in the gust front region, again, fairly rapidly in a vorticity-rich environment. A little bit later on, as the first meso is occluding in the low levels, the second one strengthening and it becomes tornadic. That's what these red lines represent here. And so that process can repeat itself fairly quickly. Dowell and others went on to note that if the outflow is weak such that the gust front can remain beneath that updraft aloft, storm may be able to cycle fairly frequently because there isn't this time required for the updraft to reform. But again, this is based on one case. I actually think that the balance they're talking about may be a factor for the persistence of two low-level mesocyclones, which we'll talk about a little bit later, and that was a case that Phil Schumacher brought to my attention. Here's part 2 of David Dowell's paper, and here they stress the importance of low-level updraft relative flow in modulating the cycling and the duration of the tornadoes. Now, keep in mind, they had very highly detailed observations of this case. This is, we can talk about this all we want and figure it out, but we can't, at the WFO level, measure this stuff. So we can develop our conceptual model about what we think could happen, but we can't get out there and measure this stuff. In this particular example here, if we look on the left, and actually in both figures, these wider gray tracks are tornado tracks. So this first one here is tornado 1, and then we see a gray track here, tornado 2, and over here is tornado 4. And I don't know what happened to tornado 3. They dropped that from the figure. But at any rate, these black arrows represent the mean wind over the lower portion of the atmosphere with about a 3 to 5 kilometer diameter circle centered on that tornado. So what they're essentially showing is that when the mean wind associated with where the tornado is matches that of the storm motion, which is to the northeast, the tornado tended to persist quite a while. With time, the low-level mean wind with the tornado turned northwest, and so did the tornado track, and that one, of course, dissipated. And recall from Paul Markowski's talk on Vortex 2 that I guess most of us heard from the recording, there's the mid-level mesocyclone plays the role of that dynamic sucking. So if all of a sudden the low-level meso gets away from where that dynamic sucking is occurring, it would make sense that it would dissipate. Shortly after Tornado 1, Tornado 2 developed here, and again the low-level mean wind was carrying that tornado to the northwest, so again it didn't last very long and dissipated. Tornado 4 was larger and much longer lasting, and they found that perhaps because of a surge in the rear flank gust front or downdraft, it actually led to more of a northeast mean wind, which kept that tornado going along a track that matched the storm motion. So again, they stress the importance of this low-level updraft relative flow, which unfortunately we can't measure unless we have vortex on every storm that we have in our county warning areas. And then, so after that, a few years later, Adlerman and Drogmeyer were back at it again with some modeling studies. They had two key things that I gathered from the studies. The first one is that there are two types of cycling that they are proposing. On the top panels is the typical one, or the one that we've been talking about, where the low-level meso occludes and moves rearward, and then a new one forms fairly rapidly at the occlusion point. But they suggested another kind called non-occluding cyclic mesocyclogenesis, where you have your low-level meso as before, but instead of falling rearward, left of the occlusion point, it actually stays with the gust front, and with time weakens and falls rearward, while discreetly a new low-level mesocyclone forms farther ahead. So in the end, you don't have the mesocyclone veering or curving off to the left. You have it essentially just weakening, and a new one forms out ahead of it discreetly. I've actually seen this in our area. Unfortunately, I couldn't recall any dates to pull up any radar examples of that, but I've seen it actually quite frequently in our area. Typically, it's not associated with storms that produce tornadoes, though, and you may see why here in just a minute. So this is the second main thing from Drogmeyer and Adlerman's paper. And of course, you look at this graph and you're screaming like, what is all this stuff on here? And I'll try to make some sense out of that. Essentially what they did is they did some modeling as a function of the vertical wind shear. They changed the shape of the hodograph. They changed the strength of the shear and also the distribution of that shear within lower and middle parts of the hodograph. So let's look at this figure here. And on the x-axis, we have increasing shear from left to right. So relatively weak shear on the left and very strong shear on the right. The y-axis, we go from unidirectional hodographs to quarter curving to half circle to full circle, which we rarely see operationally. So let's take one path here and start on the lower left and just go across. So we see for a unidirectional hodograph, doesn't matter what strength the shear is for unidirectional hodograph, we see this non-occluding cyclic mesocyclogenesis. And that, again, I said kind of makes sense with what I've seen in our area in western South Dakota. We tend to have more unidirectional hodographs, and I actually do see this non-occluding type of cyclic mesocyclogenesis relatively often. Now the next thing we're going to do is start here roughly in the middle and move upwards. So we're at a, let's say, a moderate, somewhat strong shear category. And as you start out with the unidirectional hodograph, you have non-occluding cyclic mesocyclogenesis. As you get into the quarter to half circle hodographs, now we're looking at occluding cyclic mesocyclogenesis. And then finally, once you get up to the half circle, according to the modeling results, they have steady non-cycling storms. Third thing we'll do is we'll start here on the left where you have a quarter to half circle hodographs and then move to the right. You see fairly quickly you're into the occluding cyclic mesocyclogenesis, and as you go further to the right, eventually you get to steady non-cycling. So kind of synthesizing all of this into 3 take-home points from their study is that when you increase the shear, you tend to slow down the cycling, which we noted here as you go from left to right across the typical hodograph that we see in our environments, which are quarter to half circle. Straight hodographs, according to their modeling studies, always have this non-occluding cyclic mesocyclogenesis. And then finally, no index, whether it be storm relative helicity or bulk shear, is actually useful in predicting cycling behavior, the frequency of it, and so forth. So it's tough to do operationally. And keep in mind, they did not look at thermodynamics such as boundary layer RH, LCL heights, and so forth. And I think there may be something to those variables. So now we'll move on to a case closer to, well, in our neck of the woods, in Central Region, by Josh Bausted and Phil Schumacher from the 24th SLS conference. And this is kind of what got me and Phil started talking about all this. And this was actually the day after the Greensburg tornado. There were several tornadoes in southeastern South Dakota, and it was somewhat of an atypical cycling behavior. You start out where you see this low-level mesocyclone here, and it curved left, and a new one formed, and that makes sense. So as the new one's going along, you actually see one form to the left of that. And I don't know if it was a continuation, the previous circulation weakened and then re-strengthened or what. But what's interesting is you have 2 low-level mesos side by side persisting for fairly long, and then this one to the right actually weakens and one to the left continues. So not a classic case. And in some cases like this, you see where the tornado to the left can actually veer to the left and get out of the warning box. So that's something that that we need to consider. And that was another reason that I think prompted Phil to look at this. It was a very strong shear environment, and which would suggest, based on the previous studies, that there would be a longer period between cycling, and maybe that has something to do with this. Maybe the strong shear led to a better balance between inflow and outflow. We really don't know without observations, but I would speculate that this was some hybrid of occlusion where the meso to the left really didn't fully occlude and get out of the way of the storm and actually stayed relatively close to that mid-level updraft. So then the final research paper, I believe, that I looked at was for Mike French and others, and this included Howie Bluestein and David Dowell, and they looked at a case from Vortex. Well, this wasn't from Vortex. It was some other project, Amarillo in 2003. And so we'll just look at the figures here. And the storm motion was generally to the east, northeast. And what we see in the upper left are low-level mesocyclone tracks, and these are ground relative. So you can see fairly short tracks, and they quickly moved north-northwest and weakened. And eventually, with time, as they changed their direction, which is likely due to some outflow that developed in the rear flank, that's what the authors suggested, then the low-level mesos lasted a little bit longer as they were tracking closer to the storm motion. If we look at the right here, you can see L1, low-level meso 1 on the rear flank, and with time, that was simply advecting rearward because the storm relative inflow was reported to be very strong. It was actually overpowering the outflow. And then a new low-level meso formed a little bit later that strengthened, and again, that moved rearward relative to the storm ocean, and a new one developed on the front flank. But eventually, once the gust front strengthened and they had some sort of a quasi-balance, then they could get a longer-lasting meso and tornado. So here's just, I got a couple examples from the last couple of years. This is one from, I guess, the big outbreak last year. This was northwest of Wichita at around 3Z. And you see a storm that had obviously a very strong, powerful supercell. It had, I don't know what reported tornadoes were at this time, but it had two very well-defined low-level mesocyclones, roughly 3 miles from each other. And I just noticed when I was reviewing this morning, there's almost a suggestion of there could have even been a third one here. I don't know, it could be bad velocity data out in here. But these were persisting for roughly 30 minutes before it transitioned, before it would go through the handoff. And again, that's a fairly long time, and we can only speculate, but I believe it may be related to the very strong shear, such that there was somewhat of a balance. And so instead of this one that on the left that starts to occlude quickly turns left and dies, it actually hangs in there quite a while and can track nearly parallel along with the new meso, low-level meso that formed. Now, but let's just throw one monkey wrench into this. This is from April 27, 2011, the Tuscaloosa supercell and tornado. See the very well-defined hook and tornadic debris signature here. And this, when I looked at data from this day, there was relatively little cycling. They were very, very steady, and you didn't see these dual low-level mesos like in the previous example from Topeka. But what I did next then is plotted the photographs from both days, the Topeka last year in the 14th, and then Birmingham 18Z from the outbreak in April 27th. And I didn't do any translating. It's just simply the ground relative winds. And you see the photographs actually match up quite well. They both have quite strong low-level shear. There are some differences but the quadrant, the shape, and all that, very similar, which leads me to believe there's more going on than just the shear. There's obviously terrain differences between Topeka and Birmingham. The moisture profile could have been different, and even the time of day may have something to do with it. This was during daylight hours. The previous one was at 3Z. So where does that leave us? No surprise, and everybody knows this, the cycling is very difficult to predict, but I think there's a few things that we need to keep on, that we can take into account. And actually, the most important thing, I think, is that if you're observing cycling, we need to watch out for the tornadoes that turn left, and also the so-called handoffs between the left and the right turning tornado. And sometimes we'll get new tornadoes forming far to the right on that gust front, as in the David Dowell model. So what that would suggest is that if you're the kind of person that likes to have the big severe thunderstorm warning, and then you put a little tornado warning box in the out just to track that tornado, you're kind of living on the edge a little bit dangerously, because you could have a tornado curving left out of your box. You could have a new one developing discreetly in the gust front to the right. So to me, that's the biggest key out of all this, since we don't really have a good handle on the periodicity of this and when and how they may form. That really comes into play in drawing polygons. And of course, all of you in the farther southeast of Rapid City have a better handle on this than I do. The strong low-level shear and the curvature is suggestive of a slower occluding process to the cyclic mesocyclones based on the modeling, and also the examples we saw from Phil and from Wichita, where you had two low-level mesocyclones persisting for quite some time in a stronger shear environment. So maybe there is some sort of inflow-outflow, the balance that's occurring that's leading to these longer-lived tornadoes, which, again, we don't have the instrumentation to be able to detect that. So and that's what I speculate was going on in the Sioux Falls and Wichita cases, which, again, kind of got me prompted to looking into this. So here's all the papers that I went through to review this. I have the Don Burgess's highlight in blue. And if you remember, most of us probably remember the E.F. Hutton commercial. When E.F. Hutton talks, people listen. Well, when Don Burgess writes and when Don Burgess speaks, people should listen, because he does pretty darn good work, and his model from back in 1982 holds pretty darn well to the state. So with that, I'll be glad to take any questions you may have.
Thank you, Matt. Any questions?
Hello, this is Ryan Husted in Goodland, Kansas. I had a question. You kept referring to, maybe strong shear is causing these mesos to cycle slower. You brought up the April 27th Tuscaloosa tornado. I was actually working that day in Memphis. My question was, what about storm motion? Because those storms on that day were moving 60 to 70 miles an hour, and in the Memphis area we had a tornado, F3 I think we rated it, that was on the ground for probably 65 miles, and then it cycled and it put down the F5 in Smithville, and that one lasted 30 miles or so, both on the ground 45 minutes to an hour or so at least. So I was wondering if the storm motion of the storms might be a factor in helping with that inflow-outflow balance.
Oh, that's a real good point, Ryan. I didn't look into that, but I do believe that could be the case. Dan Miller brought up a good point to me, I guess last week, on the storms in North Texas back on the 15th of May, and they were moving fairly slow, and they had some relatively frequent and erratic cycling-type behavior. So I don't have the answer to that, but it certainly makes sense to me what you said.
Okay, thanks. Yeah, I was watching those North Texas storms too, and that Granbury tornado was only on the ground 5 minutes, maybe like 3 miles or so. So, all right, thanks for the answer.
Yeah.
Hey, Matt, it's Jim Ledoux.
Hey, Jim. How you doing?
Oh, pretty good. Yep. I was really intrigued. I actually didn't read the second Adleman paper, and looking at that, I remember coming across for it, and I never read into the details about how they did that modeling study with the non-occluding and occluding cyclic mesos. And I was wondering if they had any, or if you read about what kind of microphysics scheme they had.
That I don't recall. I'd have to defer you to the paper. I'd have to look that up. The takeaway was just making small variations can have a big effect. And of course, whether or not they had warm rain or had ice processes, I assume they tried both, but I'd have to go back and look at that detail.
Yeah, because I know Dan Dawson recently is really pouring into the impacts of the microphysics and what they do to storms.
Yeah, I'm familiar with some of his work. And do you think that's related to the cyclic process?
I would imagine. Just thinking about how it modulates the strength of the cold pool, and if you have, if one model is just doing warm rain and another one's doing ice, or one's doing ice, but then all the ice gets carried away and then leaving weak cold pool instead of strong, I could imagine the outcome be pretty different.
Yeah, and I think that just drives home the point of how difficult it is to predict the periodicity of the cycling. And Adlerman basically just looked at the shear profile, so ignoring the thermodynamics and the variations of the microphysics. And obviously terrain. I think terrain may have something to do with it as well. What part of if you're flat or hilly, that could have an effect.
Yeah, that would be interesting to see. I know Texas a couple weeks ago had, the Fort Worth office had a little bit of a difficulty with their cyclic mesocyclone. I remember, was that big one that was just south of Fort Worth, produced the F4, and it moved straight left of the supercell track and went right out of there, right out of the warning polygon. They put a new one up just in the nick of time.
Yeah, that's an interesting observation, and that fits with what David Dowell showed in their I think it was the part 2 of the 2002 paper, was that the low-level advection kind of really drives where that tornado is moving. It's a big driver of it. I've been chasing before, where I'm on the the tornadic circulation, and the upper-level meso is moving away from me, and when that tornado finally dissipates, I have to go a long ways just to catch up with the storm, and it seemed to be separating, if you will, from the parent storm. So, what's driving that low-level advection seems to be key. But again, it's something you can't measure. You have to react to from a warning forecaster standpoint.
Yeah.
Hey, Matt and
well,
Jim.
I'll break off for now.
Thanks, Jim.
Matt and Jim, this is Dan in Wichita, and kind of continue that conversation. I know I've seen several cases where it's almost like there's some kind of effect where I see like a zipper effect where there's not a mesocyclone-produced tornado. There's the tornadic circulation with the cycling effect, but then I start seeing several instances of almost like a landspout along that advection line. I've visually seen this a couple times out chasing. It's a kind of a, you've got the mesocyclone tornado, and then you start, it seems with these cyclic storms, you start seeing these almost little satellite landspouts along the flanking line, and depending on what kind of advection's going on. So it's all kind of not sure what's going on there, but I've seen that visually several times.
Yeah, Suzanne, that might fit with what David Dowell was talking about with additional tornadoes forming along the gust front surge. So, I guess that would make sense. They'd be more of the so-called landspout variety, but maybe not all of them, but if they're forming where you have a lot of vertical vorticity already present along that boundary. But, of course, that just makes things all the tougher, again, if you have a small polygon because you have these things developing outside of your box.
Any last questions from Matt? Matt, thank you very much for your presentation today. We sure appreciate it.
You're welcome.
And thank you, everyone, for joining us today. And we'll see you next time. Thank you, and have